Hello, Year 11. We're going to do another lesson on vectors today. There's one or two tricky bits in this, so listen carefully, have a pen and paper handy. I'm going to go through some examples with you, and then I'm going to let you try a few for yourself. Okay? So, speed and velocity are two words that are often used to mean the same thing. There is a difference. Speed is a scalar, velocity is a vector. So they both have the same equation. We can both use this equation here, which is velocity equals distance over time. You can use that equation also, speed equals distance over time. Okay? So they're very, very similar to each other, but let's highlight this. Velocity is a vector and speed is a scalar. So there is a difference between the two. Let's have a look at what we mean by the difference. So if you consider something to move in a circle, so we've got a little black square here moving in a circle. Now, you could imagine that you're whizzing something around on the end of a piece of string, like a conker on a piece of string. The speed at which it goes round is constant. The speed is constant, and the speed is represented by the length of the blue arrow. So look at the blue arrow. You'll notice that the length of it doesn't change, and that's because speed is a scalar. It only has magnitude. And magnitude is represented by the length of the arrow. That doesn't change. So it whizzes around with a constant speed. However, look at the direction of the blue arrow. The direction is constantly changing. And because velocity is a vector, it has magnitude and direction. Okay, it has magnitude and direction. Because the direction is always changing, the velocity is changing. Okay, so let's just highlight these 2 points. When something is moving around in a circle, the speed is constant because the magnitude is constant. The length of the arrow stays the same. But the velocity is always changing because the direction of the arrow is always changing. Okay, so subtle difference there. Yes, we use the same equation for speed and velocity, but they do mean slightly different things. Now we can apply these ideas to a situation like a car going round the bend. And what I want you to look at here very carefully is the little red arrow down here, right? Now that arrow represents the velocity vector of the car. So when the car is coming down, the arrow points down, and when the car is going to the left, the arrow points to the left, and it changes direction as the car changes direction. The length of that red arrow represents the speed of the car, and the length doesn't change. So we say that the speed is constant because the speed represents the length of the arrow. It's a scalar. It's constant. It doesn't change. But look at the direction of the red arrow. The direction of the red arrow is changing. It was down and it swings around to the left. And velocity has magnitude and direction. Therefore, we say that the velocity is changing. Okay? So that's an application of it. Let's move on to the next slide. Now we're going to look at force vectors. Okay, so we've looked at two types of vectors. In fact, in total, you'll need to know 3. So they are displacement vectors. That's the first one we looked at, and that was last week. Displacement vector was the first one. The second one that we've just looked at is velocity vectors. The third type of vector that we need to look at is a force vector. So we can represent forces with arrows. You've been doing this all through Key Stage 3 and Key Stage 4. So we can represent Okay, there's an arrow, and we can represent that as a force. We could say, well, that's 30 newtons, and it's going up and along. Okay, let's say there's an angle there of 40 degrees. So you might say there's a force of 30 newtons at an angle of 40 degrees. Okay. Now, the higher tier have to do some extra things, which I'm going to go through with you. One of the things that we have to do is that we can break a single force down into two components. Okay, and this is called resolving. It's called resolving the force into two components. And we do this using a scale diagram. Okay, so you'll notice down here it's a scale drawing. So let's have a look at some examples of what we mean. So these I'm going to do two examples with you. They're both taken from exam papers. This diagram shows a boat towing a smaller dinghy. Okay, so this is the boat, this is the dinghy, just in case you didn't know. There's a rope here. Look, there's a rope attaching the two together. There's a tension. So as the big boat goes forward, it creates a tension force. That rope goes taut. There's a force in the rope which pulls the dinghy. We're given some information about the force. We're told that the horizontal force forwards is 150 newtons and the vertical force is 50. So if you look at that rope carefully, it goes up slightly, doesn't it? So it pulls that way with 150, and it actually pulls up as well with 50. Okay, these two things here are what we call the two components. We've got the horizontal component and the vertical component. The next thing we have to do is to draw a vector diagram to determine the magnitude of the tension force in the tow rope. So let's look at how we do that. So we need a piece of graph paper, and this graph paper is given to you in the question. Now, this looks a bit complicated, but it's quite simple, really. So let's just recap. There is a tension force in the tow rope causing a horizontal force forwards and a vertical force upwards on the dinghy. And here are the two components. The horizontal component is 150 and the vertical component is 50. We're going to draw a vector diagram on the graph paper, okay, and we need a scale first. Okay, so I've given a scale here. 1 centimeter is 10 newtons, and that means that I can get 15. It will fit on this diagram now. So let's draw. Okay, let's draw on here what we mean by the horizontal component. So I've got my starting point over here. This red dot is the starting point. The horizontal component, then I'm going to draw that in there. That's 15 squares, because I said that 1 square is 10. I need 150 newtons, so that's going to be 15 squares. Okay, you can count the squares if you want. There are 15. And then from the end of this, from the point of that vector, we're going to add the vertical component, and that's 50 newtons, so that's 5 squares. Okay, so here are my two components, horizontal and vertical. And remember how we draw the resultant. The resultant goes from the start. Okay, so we go down here from the start up to the end. Okay, so let's get rid of that. Now, we need to, this is a scale drawing. Okay, now in a real exam, you would have, in your pencil case, you would have a protractor and a ruler. So let's measure, first of all, the length of this line. So I've got this graphic here of a ruler to scale, and it's telling me that the length of this is about 15.7 or 15.8 centimeters, if you can read that. If I highlight that for a second. Okay, here that is about 15.8, I think. Looking at that, it's not totally accurate. That's the length of it. Now let's get rid of the ruler, because the next thing we have to do is to measure the angle. So let's move the ruler and let's have the protractor. Now I want to measure the angle. Okay, because it's a vector, it has a length, it has a magnitude, but it also has a direction. Okay, so I need to look carefully here, and I can see that's 20 degrees according to this protractor. So you do need to have in the exam, you need to have a clear plastic transparent ruler, and you need a clear plastic transparent protractor. Okay, so let's put the answers there onto. So because the length of that was 15, that was 15.8 centimeters. That means that if I multiply that by 10, because my scale 1 centimeter is 10, that means that my tension is 158 newtons, and then the direction is 20. Okay, so that's how we do that. Let's have a look at another example. So move on to the next question, if it'll let me. Not sure it will. Okay, here's the second example. Similar in some ways to the first one, except boats. Now we've got aeroplanes. We've got a small aircraft towing a glider. Okay, we're told this time, we're told what the resultant is. We're told that the tension in the cable, so here is a cable, one pulling the other, we're told that that is 2,000 newtons. We're told that this here, oops, let's get a decent colour. We're told that that is 2,000 newtons. We're told the resultant is, and we're told the angle is 20. And then it says, draw a vector diagram. Oops, wrong colour. It says, let's draw a vector diagram to determine the magnitude of the two components. So we're going to do it the opposite way round this time. We're starting with the resultant, and we're going to work out the horizontal and the vertical component. This question is very similar to the last one. We're going to draw a scale diagram of the vector linking the planes together. But this time we're going to start with the resultant and work backwards to find the two components. So looking at the information given to us, we can see that we have a tension of 2,000 newtons at an angle of 20 degrees. So we need a force vector of 2,000 newtons at 20 degrees. Now the scale I'm going to choose for this, well, 10 squares equals 2,000 newtons. So therefore 1 square equals 200 newtons. So that means I need a 10 centimeter line at 20 degrees. So let's get the protractor. So protractor on there. Let's make a mark at 20 degrees. So this is the method that you would use. I need a mark there at 20. Let's hide the protractor and get the ruler. And I need another mark at, so that's, I know the ruler's at 20 degrees there, and I need to draw a line up here to 10. Okay, so that's my 2,000 Newton vector at 20 degrees. So let's hide the ruler again. Now I can draw a component there. So I know now that's the right length and the right angle. So in order to find the two components, I need to sketch along here and form the triangle. Okay, now so it would look something like that. Obviously I need to do it a bit neater than that. So I'm going to, that's just to give you an idea of how it's drawn. So I'm going to put my horizontal component in there, which is 9.6 centimeters. And I've got my vertical component there. Now there is a mistake there. 3.7 centimeters should be, that's 740. If you multiply that by 200, that is 740 newtons. So my two components are 740 newtons vertically and 1,920 newtons horizontally. And that's the sort of method that you would use to find the two components of a vector. So thank you for listening. Maybe play it again just to get your head around it, and then we'll have a go at some practice examples. Good luck.